Lesson 39 is all theoretical, no math here, but once again, super interesting. Ernest Rutherford, the Rutherford planetary model. So right now we've got the model of the atom. We've got the plum pudding model. Oh, whoops, that's not an atom. Big blob of positively charged material, and then negative things in there to balance it out to become neutral. That's the present model of the atom at Rutherford's time. What Rutherford did was he was concerned with alpha particles. Alpha particles we know are helium nuclei, so it's a helium atom with the electrons, He, 2 plus. In other words, it's 2 protons and 2 neutrons. And alpha particles are released by radioactive materials. So what he did was he took these alpha particles from so we got a lead box, which is a radioactive substance, and radioactive substances decay, and lead gives off alpha particles. And he shot these alpha particles through a very, very, very thin piece of gold right here. And then he had this detector here, a screen coated in zinc sulfide, and the alpha particles would go through here, and then they would hit the screen over here, so he could detect where these alpha particles ended up. And what he expected, or what everybody expected at that time, was that if the plum pudding model of the atom was true, then most of these alpha particles would just appear on the screen over here, or with slight deflections. It says here, the plum pudding model was correct. The positive charge of the atom is spread out evenly over a relatively large area. This would mean that the effect of the positive charge would be very weak on other charges because it is so spread out. The negative electrons are unimportant since they're spread out all over the place, spaced out and tiny. This would result in very small, if any, scattering angles for the alpha particles, since the alpha particles would just sail through. So that's what he expected, but that's not what happened. In fact, this kind of thing happened here. Include in blue. So most of them were actually deflected at small angles, but some of them were deflected at insanely, if I extend this, some of them were deflected at extremely large angles, and some of them even kind of almost bounced back at themselves. And said the actual results surprised Rutherford. And what he determined from this, from these alpha particles bouncing off of very large angles, before we say that, just read this right here. Rutherford described this in a lecture I was saying it was almost as incredible as if you had a 15-inch shell fired, a 15-inch shell at a piece of tissue paper, and it came back and hit you. So the results he got from his experiment were so surprising that there could only be one. Oh, good, we got a PhET demo. Let's have a look at the PhET demo. Sorry, I should have set this up before. Download. Ding, ding. Here we go. So here's a PhET demonstration of Rutherford scattering. Well, here's the plum pudding model. Right, there's the plum pudding model. That's alpha particles. Yep, so that's what you would expect from the, let's give them a little bit of energy. Yeah, we'll put traces on them, see. So that's what you would expect. Now, but here's what happened with Rutherford. Where's Rutherford? There you are. There you are. Oh, it's different. They've changed it. Okay, there you go. There we go. So you can see most of them are going straight. Some of them are being, oh, they've changed it since last. Let's put the trace. So trace. Yes. There we go. Now you can really see it. So most of them are kind of going straight. Some of them being deflected a little bit, but some of them are being deflected at these wild angles. Why are they being deflected at these wild angles? remember that alpha particles have a charge of +2. So the only way that they're not hitting the nucleus here, this is the discovery of the nucleus, they're being deflected electrostatically from the nucleus. So when this positively charged alpha particle comes near the nucleus, it is going to be heavily deflected because the nucleus is positively charged, or not positively charged, has protons in it. So they're going to repel the positively charged alpha particles. So Rutherford's explanation for that. Oh, and let's do this. Let's minimize the number of neutrons. So now you're going to see him deflected even more, maximize the number of protons, because now the nucleus is all protons and very few neutrons. Okay, that wasn't as dramatic as I thought it was going to be. Anyway, there it is. Back to our lesson. So this was the birth of the planetary models. Rutherford theorized that the atom must have a really dense, small, positively charged nucleus. That's why it's called the nuclear model. And then the electrons are orbiting around it at great distances, like immense distances. Like, for example, if this is the nucleus of an atom, the electron, I'm standing here in the classroom, then the nearest electron would probably be over by Vivo. So you've got this huge amount of empty space within the atom. You've got this this is relatively massive, very dense, intense nucleus, and then a great amount of empty space, and then the electrons orbiting it. So this is the planetary model, Rutherford's planetary model, and it was extremely innovative, except for some things that had to be worked out. And these were the shortcomings of the planetary model. If you've got electrons orbiting a nucleus, electrons orbiting a nucleus, then they are by definition accelerating, and they should be losing. So in fact, if the electrons release EMRs, they're releasing photons. Any accelerating charge will create EMR. As the moving electrons release EMR, they are releasing photons of energy. This means the electrons are losing energy. So if they're losing energy, they should spiral in and crash into the nucleus. But that doesn't happen. So that was one of the weaknesses of the planetary model, and that shall be answered in the next couple of lessons.